One of the key points that I want to make along the way when we're doing all of these additions to alkenes is that you have a series of reactions that all share the same mechanism. And if you're trying to memorize things, then you may miss the fact that these two problems are fundamentally the same. It's just that in one case, you have to do is add in a concept that we used earlier in the course, which is once you form the cation, then resonance will be involved, and then things get a little bit more complicated. And so if you have to memorize this as a separate problem, then you're substantially challenged if you recognize that it's just simply one concept you just recently have learned and should be able to apply with another concept that you learned a long time ago and again should be able to apply. Then fundamentally this is not that different. These are exactly the same problem. So mechanistically, of course, you would start a hydrohalogenation by having the double bond serve as the nucleophile and attack the H, lead to the Cl breaking off, which will form the more stable secondary carbocation over the choice between the secondary and the primary, and then the chloride comes in and attacks the carbocation, and that leads to your racemic mixture of products, wherein you make both the up and the down version of the chloride. Again, the Markovnikov product, in other words, attack on the more stable carbocation. With this material, there is no difference between the two double bonds. That can introduce some complexities, but either one of those double bonds can start exactly the same way. What you're going to do is attack the hydrogen to begin with, which causes the chloride to leave, and generates Cl-. The initially formed cation will be the secondary carbocation, but that can be stabilized by resonance, and you can think of forming a primary carbocation plus resonance or a secondary carbocation plus resonance. Of course, I would prefer that you not think of it as two different resonance contributors, but instead as a single resonance hybrid. And the resonance hybrid has a methyl at this end, so that's not involved in the resonance, but then you have the plus on two different spots. This primary end, which with a relatively small delta plus, and the secondary end with a much larger delta plus. And that is, again, because the secondary can tolerate having a bigger delta plus on it. And so you would like to think of it this way. Now, mechanistically, we have generated Cl-, so that is floating around, and it can now add into one of the two positions. If the chloride adds to the secondary position, that should be a relatively faster intermediate to form, and that is because there is a larger delta plus at the secondary position in the resonance hybrid. So if you attack a resonance contributor, you draw it that way. So mechanistically, drawing it this way would be fine. If you are instead to attack the resonance hybrid, you would draw it this way. Either way, you will lead to the same place. One of the two products that you are going to form is going to be this racemic mixture, and again, you should note that this is going to have a terminal double bond, and so that is a relatively less stable double bond that you are forming. However, this should form faster because you are attacking the area of greater delta plus, and so this would be your kinetic product. The other alternative, of course, is that the chloride could attack at the primary position, and that should be a relatively challenging thing to do because there's a smaller delta plus at that position. However, once you have attacked there, then it will lead to this single product that contains an internal double bond, and therefore is the thermodynamic product because, again, it contains the internal trans double bond. So this is a more stable product overall, but it should form relatively slower because it is more challenging to attack the smaller delta plus than it is to attack the area of larger delta plus. And so thinking in terms of a reaction coordinate diagram, what we have here is starting at a certain energy, going until you reach a common intermediate, and then from this common intermediate, you're going to lead to two products, the lower energy of which is going to be the thermodynamic product, the one with the trans internal double bond, the higher energy of which is the terminal double bond. So you're leading from the starting material to the common intermediate, which is the cation, the resonance stabilized cation, and then we have the trans internal double bond product here, and we have the higher energy terminal double bond here, but the hump to get to the terminal double bond is relatively lower because that is your kinetic product, and the hump to get to the final lower energy product, the trans product, is higher. And so this gap down here is the difference in energy between the trans and the terminal, between the thermodynamic product and the kinetic product. This is the gap in energies, but the gap in kinetics, how fast it happens, is determined by the height of the two humps involved. And you might see that in, say, the Miller handouts described as delta G double dagger, whereas this right here might be described as delta G. What's different fundamentally about the two problems is the fact that you have the possibility of attacking either of the two spots. But mechanistically, that's nothing more than the same initial step plus resonance. So you generate one of the cations, this one first, and then you recognize that resonance exists, and so you have to draw both of them. But then the chloride can simply attack either of the pluses and lead to these two products. So if I'm asking for a predict the products sort of question, you need to draw both of these products. If I'm asking for for a mechanism, then you need to draw a mechanism that explains the formation of both of those separately. And you only ever need to draw the reaction coordinate diagram if I'm asking about kinetics versus thermodynamics and having you diagram this out. And I would hope that you would recognize that the thermodynamic product is formed on the basis of alkene stability, but the kinetic product is formed on the basis of the resonance hybrid that gets attacked.